In this video, I would like for us to look more at the gradient of a differentiable scalar-valued function of multiple variables. In a moment, I'm going to talk through the general theory behind the driving computation in this video. But before we do that, I just want to give you a picture of the objects that I'm going to refer to so that as we talk through the general statement, you can map them to something familiar. So in this graph, I have sketched, well, I didn't sketch it, it's a computer picture, the paraboloid z equals x squared plus y squared. So you can think of that as the graph of the scalar valued function of two variables. Say this is the surface z equals f of x and y, where this function is x squared plus y squared. Imagine that we are interested in all of the points in the domain which send us to one particular value for this scalar valued function. So since the outputs here are just numbers, I can say, what points from the xy plane send us to a z value of 4? That would be like taking this paraboloid and intersecting it with the plane z equals 4. That's what I've imagined here, this yellow curve on my surface. That's the intersection of z equals 4 and this paraboloid. What's the family of points in the xy plane which sends us there? Well, that's this circle down here in the xy plane. In fact, if you picked different output values starting at 0 and going up, you'll recognize pretty quickly that if you take any, say, number k, and look at what points in the xy plane send you to that output value, what you will generate in the domain is a family of concentric circles. These are what are called level sets for the function. So for this particular function, the level sets are curves. So if your domain is two-dimensional, you might use more specific language of level curves. And this particular family of level curves or level sets, to speak more generally, is a family of concentric circles. If, just to mention the other kinds of vocabulary that you encounter, if our function was a scalar valued function of 3 variables, then the domain would be in R3. And in that context, you may use the phrase level surfaces. So the general expression is level sets. In R2, you can talk about level curves. That's what we're looking at in this picture. The curves are the concentric circles. And then if our domain is three-dimensional, R3, we may use the language of level surfaces. The analog for this function in R3 would be x squared plus y squared plus z squared, in which case the level sets would be concentric spheres. So this would be level surfaces. Okay, the other thing I want to mention in this picture with this specific function before we move on is what the gradient of f looks like, in particular where we should picture it. So here, the gradient of f is the vector 2x, 2y. Let me give you a moment just to think about this. What is the dimension of this? Where in this picture does it live? I really wanted to emphasize that question of where does the gradient of this function live, because it's a common misconception I see with students doing multivariable calculus computations. This is a scalar valued function of 2 variables. So we have 2 inputs and 1 output. The graph of this function is the set of points x, y, and z in 3-dimensional xyz space, satisfying x squared plus y squared equals z. So the graph of this function is in R3. But when you do the gradient, you are just computing the partial derivatives of this function with respect to the 2 inputs. So this is a vector in R2. And that is a general statement. If you have a scalar valued function of n variables, the graph of that function you want to imagine as a set in Rn plus 1. However, the gradient of that function is a family of vectors. In fact, if you can see them in this picture, I've sketched scale versions of them in red. It might be hard to make out against the black, but the family of vectors that you get, the vector field you generate when you compute the gradient of f here, is a vector field back in the domain. So sometimes I see students try to imagine the gradient on the surface, and that's not really what you want to picture. You want to imagine that the gradient is back in the domain. So that's one thing I wanted to emphasize, but really the first major conclusion of this lesson is that the gradient of f is perpendicular to the level curves in this case. That's something that we'll work through in just a moment in generality, but in this particular picture, 2x, 2y at any point, say I'm right here on this level set, this level curve I've emphasized here. If I'm right here, then whatever the xy coordinate of this point is, my gradient vector is twice those coordinates, so 2x, 2y. So I wanted to sketch this vector starting at the origin and kind of radiating outwards. It would go from the origin to that point, but then actually be twice the length. So it could be kind of like this. Sorry. Okay. So that's one thing, is that the gradient would look like this. Anytime you are trying to visualize a vector field, though, especially if you're doing it with a computer like I've done in this graphic, you rarely sketch the vectors at their true lengths. So if you compare the vector I just sketched to the little red vectors, it's much longer. And that's because vector fields are usually scaled down in computer graphics. The actual true length of the vector is rarely as important as its direction. That's usually more important, and also just its relative length compared to neighboring vectors. So it's pretty common for vector fields in general to be scaled so that you don't have too much overlap and you can squeeze more vectors in your picture. If I drew all these vectors to be the same length as that, the picture would be very crowded. Okay, so the length of this vector isn't so important in this image, but what is important is if you look at how this vector relates to the circle for which we are saying that this is the gradient of this point on that circle, it's perpendicular. Okay, so if you have a scalar value function of n variables, which is differentiable, so you compute the gradient is a vector that lives in the domain. And as we will work through mathematically in just a moment, this gradient is perpendicular to the level set containing the point where you've computed the gradient. So you're computing the gradient at a point. Whatever level set contains the point, the gradient vector is perpendicular to that level set. So I'm emphasizing that this is a point-based computation here, but the general phrase is gradients are perpendicular to level sets. So now hopefully that illustrates what this looks like for this particular function. Let me now get rid of this example, and we will just work in generality for a moment before looking at applications of how we can use this statement, the gradients are perpendicular or orthogonal to level sets, to actually get some information. Okay, this is just going to generalize the conclusion that we reached a moment ago with our function f of x and y was x squared plus y squared. Again, let f be any differentiable scalar-valued function of n variables, where n is at least 2, so that we have multiple inputs. Then, because f is scalar-valued, its outputs are scalars, imagine we take such a scalar output k and compute what is ultimately a preimage. So this is a subset of the domain consisting of all of the points in the domain which get mapped to k. This subset of the domain is like the circles that we had for our paraboloid a moment ago. So here, for some fixed value k, this is one of the level sets for this function. Now it's like, okay, just grab a point like I did a moment ago where I just highlighted a point on one of those circles. So choose any p from this level set where the gradient of the function is non-zero. And the thing is, I'm about to conclude that the gradient is perpendicular using a dot product. And it's like, okay, if the gradient was 0, it would be, you could call it perpendicular to everything because it would have a 0 dot product with everything. So here we're really just saying focus on where the gradient is interesting, where it doesn't vanish. I want to imagine that if I have p, and this is a point in some level set for my function, then imagine I have a differentiable curve passing through P, which is contained in the level set. So going back to those concentric circles, you could imagine parametrizing the entire circle, if you like, and calling that R, or you could just parametrize like an arc of the circle passing through the point where you're interested. I don't want to spend too much time on justifying that you can do this. So if you're wondering, like, how do I even know that there is such a curve, R of t, a parametrized curve, passing through P entirely contained in the level set. So how do I even know I can do that? There's some theory there. It involves something called the implicit function theorem. And I don't really want to get off topic by kind of going into that. So let's just suppose that we can do this kind of for argument's sake. So imagine that you can kind of do like a circular arc from a moment ago, passing through P contained in the level set. Okay, all that to say, what does it look like to do f of r of t? So imagine that I evaluate my function along that curve. What does it look like, right? So r of t is entirely contained in the level set we described here. So when I plug all the points on this curve into f, so when I do this composition and I evaluate f along this curve, it's a constant. I want to write the constant on the left here for a reason. It's the constant value k. Okay, so this is just a constant statement. Notice here that this is a parametrized curve. It's a function of one variable, and f is a scalar-valued function. So ultimately, this composition is a map from one-dimensional parameter space, you can think of this like t in R, to R. So this is a function with one input and one output. Therefore, its derivative is actually going to be a one-by-one expression because this is kind of like differentiating a function of the form y equals f of x. Okay, so what are we going to do? We're going to differentiate both sides of this with respect to t. So I'll do d dt of the left-hand side and d dt of the right-hand side, and this is just plain old differentiation with respect to t. It's not a partial derivative or anything like that. Let me give you a moment to do this. So this is a composition. You want to differentiate it with respect to t, and in particular, at the end, you should be able to look at that and say the result is a scalar. We need to differentiate a composition. So if you're not really sure what you should be writing down here, if nothing else, just go straight to the chain rule. That will be df, where that's like a general Jacobian expression evaluated at r of t, matrix multiplied with dr at t. The thing is, f is a scalar valued function of n variables, so this is a 1 by n row. R is a vector valued function of one variable, so it's a parametrized curve. This is an n by 1 vector. This matrix times that one, so 1 by n times n by 1 is a 1 by 1 scalar as we wanted to see. And also, there's just a more specific way to write this matrix product. If I take this 1 by n row and transpose it into a vector, an n by 1 vector, it's the gradient of f. That's really what we're interested in this lesson. This is n by 1. It has all the same coordinates. It's just the dimension is flipped. So what here is a formal matrix product, you will convert into a dot product when you do this transpose action. So it's like this matrix product now becomes a vector dot product, and then dr is just a general way of saying the velocity vector, which you can write more specifically as r prime of t. Okay, so this is what I would like to see on the right-hand side. It's a vector dot product, and what is this dot product equal to? The derivative of a constant, so that's 0. Let me just write that over here. Okay, so differentiating a constant, of course, is 0, as it always is. Now we can conclude that 0 is the dot product of these two vectors. Well, if two vectors have a dot product of 0, it means that they are perpendicular to each other. If I try to picture that here, okay, let me see if I can squeeze r prime, but r prime is the tangent velocity vector. So that's like this. And then the gradient is either pointing this way or this way. Let me point it this way for the picture. Here, I'm actually imagining that I'm at the moment where t equals 0, but this is true along the curve. Okay. R of 0 is p, so this is really the gradient of f at p. So the gradient of f at p is perpendicular to this tangent velocity vector because we've just proven that they have a dot product of 0. That's the complete story when we're looking at level curves, like we had a moment ago with our paraboloid, because I only have one sense of direction that I can use to pass through P if I'm living on a curve. If you are looking at a surface, then what you can do is say, okay, parameterize one sense of direction, but then you could also take a different curve at a different angle through P and get the same result. And ultimately, what you can show is that the gradient has to be perpendicular to all tangent senses of direction, which means that if you imagine like a tangent plane, the gradient is perpendicular to that. So the general conclusion that I want to extract from this computation is that the gradient of f at P is perpendicular to the level set containing P. That's just nice theory to know in general, but it has a lot of applications. And what we will do for the rest of this video is talk about how you can use this statement that gradients are perpendicular to level sets to actually write down tangent lines, tangent planes, in general, do like kind of cool first order approximations. What we are going to do now is take the knowledge we've just arrived at, which is that if you look at a scalar valued function, the gradient of that function at any point in the domain is perpendicular to the level set for that point, to write down what you could think of as tangent lines, planes, first order approximations. All right, I'm a little bit nervous to do this because I feel like every time I teach this concept in class, I'm not sure it sticks. What I would like to do is try to work through this derivation with you right now. I've done some color coding. I'm not sure if that's going to be helpful or not, but I hope it helps. If you are completely lost by the end of this explanation, keep going and watch the first example. So what I might make seem very complicated right here is actually not that bad in practice. So watch the first example, and then when you see how we actually use what I'm doing here, you can come back and watch it again, and maybe it will make more sense the second time around. So kind of let it soak in and see it in action before you write it off. Okay. What we are going to do is imagine first that we have a scalar valued function of n variables, which is differentiable at some point in its domain, call that point P. G here is a function of n variables, which is scalar valued. So I've written this kind of general notation that xn plus 1 equals g of x is how we can think of this function. What I mean by that is like, if it were a function of one variable, we could say y equals g of x. If it were of two variables, z equals g of x and y. If the domain for g is three-dimensional, we could write this as w equals g of x, y, z, etc. Since I don't actually know what the dimension is, I'm just going to say call that like new letter, the z, w, whatever, call it x sub n plus 1. For such a differentiable function, we already know how to write down the first order approximation. We have it here. So that is our familiar, like what you would think of as a tangent line or a tangent plane for a function of one or two variables respectively. That means that what I'm about to explain, we don't need because we already have a way of writing down the first order approximation. What I'm going to do is pretend I don't know this and get to it again by using this new idea of gradients being perpendicular to level sets. It seems silly to do this because, again, we already know how to do a first order approximation, but this method generalizes in a very nice way to give you the ability to write down, say, a tangent plane in the context where you wouldn't be able to do it easily with this approach. We'll have examples so that you'll see what I mean by that. So I don't want to start describing that in words right now. We'll see examples in just a moment. So what I'm going to do is define out of thin air. I'm just going to create on the spot a new function, which I typically call h in this context. The dimension of the domain for h is n plus 1, because h is going to be a function of x1, x2, x3, all the way through xn, and then also xn plus 1. Here where I have xn plus 1, think of that as just general. Don't think of that as the output for g specifically. It's like, sorry, again, I really hope this sticks, but I hope I'm not kind of sending you in circles. If our function here is z equals g of x and y, we would just say h is a function of x, y, and z. Its dimension is perhaps all of R3. Sorry, the domain is perhaps all of R3. Okay, so that's what I mean by the xn plus 1 as it appears there. What we're going to say is that's just g minus xn plus 1. It could be something like g of x and y minus z. All right, why would we do this? The idea is that every point which we could think of as living on the graph of g, so every n plus 1 tuple x1, x2, x3, xn plus 1, which makes this equation true, where the n plus 1th member of the point is g of the first n members. So every point that satisfies this lives on the level set h equals 0. So it's like the graph of g, we can now think of as the graph of the level set for which h equals 0. That means if I want to come up with some kind of tangent plane analog for g, I can use the fact that the gradient of h will be an orthogonal sense of direction. So we'll write down vector equation of a plane in just a moment. Because I'm running out of space already, let me take this definition of h here and use it to immediately write down the gradient of h just in general. So the gradient of h anywhere in Rn plus 1, you would compute by computing the partial derivatives of this right-hand side here. You know what? I think I'm going to pause and let you, instead of just doing it for you, let you see if you can do that yourself. So try to think of what the gradient of this expression should look like, and first maybe write it out with a lot and see if you can condense it down. Before I step away, let me explain my color coding. I haven't actually done that yet. Blue here represents n tuples in the original domain for G, so that's Rn. And then the yellow is scalars. So what I want to emphasize here with the inputs for H is that that's just an n plus 1 tuple. It's the vector x from Rn with this n plus 1th coordinate kind of tacked on at the end. Okay, without thinking about G, forget about G for just a moment. Go ahead and compute the gradient of H. The gradient of H that you wrote down should be a vector with n plus 1 entries in it, where each of those entries is the partial derivative of H with respect to each of these inputs. So what is dH dx1 in order to get the first component of the gradient? I need to take this expression and differentiate it. Sorry, I'm blocking it. Differentiate it with respect to x1. How do you do that? Well, again, xn plus 1, just think of that as a general xn plus 1, like, g of x and y could be x squared plus y squared. This would be x squared plus y squared minus z. Okay, well, if you differentiated that with respect to x, you would get 2x. So what I mean by that is the derivative of this expression with respect to x1 is whatever the derivative of g is with respect to x1. Likewise, the derivative of this expression with respect to x2 is whatever the derivative of g is with respect to x2, because xn plus 1 is just an independent n plus 1th coordinate. So if I want to do the first n coordinates of this new gradient that we're trying to write down, it's dg dx1, dg dx2, all the way through dg dxn. I could write that dg dx1, dg dx2, et cetera, but let me write it more concisely as the gradient of g evaluated at x, where this represents x right here. Like that. Oh, sorry, I wrote on top of something. Yeah, I'm running out of room. Okay. When I say x here, I mean x1 through xn. All right. What about the final coordinate for the gradient of h? It's going to be the derivative of this expression with respect to xn plus 1. That's coming just from this last piece right here. So d, this right-hand side, dxn plus 1, is the derivative of this with respect to xn plus 1. That's just going to be negative 1. Okay, so stick with my color coordinates. Perhaps I should have written this in blue. And this one is yellow. So this is n coordinates, and this is 1 coordinate to give us a total of n plus 1 coordinates in the gradient of h. Okay, that is the gradient of h in general, but now I want to imagine that I'm trying to find the first order approximation for g at p when x is p and xn plus 1 is g of p. So it's like I need to take this gradient here, plug in p for the first n coordinates and g of p because I'm looking for that specific value for this final coordinate. All right, here we go. Using the vector form for like a tangent plane, works for tangent planes, but it works in general for higher dimensional space. We're going to say that to come up with this notion of like a tangent space for the graph of this equation, which is really the graph of the level set h equals 0, what I'm going to do is take an orthogonal vector We know that now to be the gradient of h at the gradient of, at p, g of p. In coordinates, one coordinate, dot a difference vector where it's going to look like the general space coordinates, x1 through xn, comma, xn plus 1, minus p, g of p, the point where we are trying to compute the tangent space. So this dot product is 0. That's something that you derive this vector equation when you study tangent planes. It also works for tangent lines. It works in general. Here, this is an n tuple. This is an n tuple. This is an n tuple. Trying to go with my color coding. And then we have one coordinate, one coordinate, one coordinate. Okay, let me take this line now and simplify it. What I'm going to do is use the fact that we know what this gradient looks like. It looks like this. And then I'm going to combine these together. Okay, so replacing this first term, I'm going to say that this is the gradient of g at p, comma, actually this is always just -1. And then here we would have x1 minus p1, x2 minus p2, xn minus pn. In other words, the first n coordinates of this difference vector is x minus p. And then we would have xn plus 1 minus gp. This marker is giving up. Take this dot product, rearrange terms, see if you can come up with a form that agrees with what we already knew to be the equation of what I would normally call the first order approximation, but you could also think of that geometrically as like a tangent space, tangent to g at the point p, g of p. I'm worried about running out of room, so I think there's a better way for me to organize this. Let me put 0 on the left here. And we'll just say equals. Okay. I am going to do this dot product again in the interest of space. I don't want to write it down twice. I'm going to think about this and this first. Okay, I would have negative xn plus 1 plus g of p. So I'm going to take that negative xn plus 1 and go ahead and move it to the left-hand side. And then we're left with g of p. Okay, not done. But these two terms came out of this product here. So -1 times xn plus 1 on the right-hand side, moved it to the left-hand side, changed the sign, and then -1 times negative g of p is just g of p plus, so now I'm going to do the first product in this dot product. It's actually in products, but it's written very concisely here. I'm not going to try to expand this. I'm just going to write it as the gradient of g at p dotted with this difference vector x minus p. And if you compare that to the first order approximation that we already wrote down, it's exactly the same. This left-hand side is just the scalar output. So, there are n components here that give you a scalar. Here I'm calling that like a new coordinate, like z is something with x and y. Here I'm calling it the output of the linear approximation, but it's the same idea. It's a scalar quantity that comes out of doing this right here. Okay. Yeah, I think this went fine, but if I lost you at some point, I'm going to do a very straightforward example where we are going to find a tangent plane for such a function using this methodology. Once you've seen what it looks like, I think this whole explanation will make more sense to you. The beauty of this idea of taking the graph of some set of points and reimagining it as a level set for a new function is actually going to give us, again, a more powerful way in certain contexts to write down this kind of equation where we couldn't do so otherwise. Yeah, so we'll see several examples of that in just a moment. That approach I just outlined, we can now do explicitly for this example. So we have here a scalar valued function of two variables. So it's a map from R2 to R. F of x and y is 3x squared plus e to the y. We want to find the equation of the tangent plane at the point 1, 0, 4 in R3. So if you plug in 1 and 0, you get 4. Let me write down the old approach, and then we'll do the new approach in detail. So I'm going to call the old approach, which is to use the first order linear approximation that we already know, as method 1, and then our new approach I'll call method 2. For method 1, what I want to say is, what you could write as L of x and y for linear approximation. I'm actually going to write z. Just means it's the output of doing the linear approximation. It would be f of 1, 0, that's 4, plus the gradient of f at 1, 0, dotted with x minus 1, y minus 0. Oh, sorry. And if I were actually solving this problem, this is what I would do. There's no reason not to do this. But just for educational purposes, let's do the new approach. Out of thin air, I'm going to invent on the spot a new function which has a domain one dimension higher than the domain of f. So we had f as a function of x and y. I'm going to let h be a function of x, y, and z. And what it is it's going to be, say, right-hand side minus left-hand side, doesn't matter which one, but we want this equation to turn into the level set h equals 0. So I'll write that as 3x squared plus e to the y minus z. So this is just general z. But what happens is that any x, y, z, think of f over here, z, x, y, z, that satisfies this equation, when plugged into h, makes this right-hand side 0. So the graph of this, which is actually a surface, so the graph of this would be a surface in R3. The graph of this surface, you can now reinterpret as the graph of the level set h equals 0. It's the same surface, it's just being viewed through a different lens. The first time, if you just look at this, you would think of it as the graph of f. It is not the graph of h, it is the graph of a level set in the domain of h. If you wanted to try to graph h, it would be a set in 4-dimensional space, which we're not going to do. Instead, we're going to say any point z, x, y, and z that makes this true is the same thing as h sends that point to 0. Okay, now we need to do the gradient of h at the point 1, 0, 4. I think I can do this all in one step. So if you compute the derivative of this with respect to x, you get 6x. Plug in 1, we get 6. With respect to y, we get e to the y. Plug in 0, we get 1. With respect to z, the way I've set this up, just like before, it's actually just going to be negative 1. 6, 1, negative 1. Then to get my tangent plane, I'm going to do that vector dot product, where it's this vector. This is orthogonal to the plane. So I'm going to take this normal vector, 6, 1, negative 1, and dot it with x, y, z minus 1, 0, 4. So x minus 1, y minus 0, z minus 4. We want to expand that. The left-hand side will be equal to right-hand side because we're looking for this vector is orthogonal. So we compute this dot product. This is a vector that lives on the plane. This is orthogonal to the plane. Their dot product is 0. Expand, isolate z, and we'll get z equals 6 times x minus 1 plus 1 times y minus 0 minus z, that's what I put over here, plus 4. Let me rewrite that a little bit differently as 4 plus, I think I actually won't expand. I'll write 6 times x minus 1 plus 1 times y minus 0. We're done. If we compare this to this 4 is here, this z is here, x minus 1 is here, y minus 0 is here, and then the 6 and the 1 are the coordinates of the gradient, like that. Okay. So the principle is, if you want to write down a tangent line or plane for this kind of function, you basically just bring everything to one side. Call this z. Here I subtracted z over to the right-hand side. Set it up as h of x, y, and z is 3x squared plus e to the y minus c. Took the gradient, plugged in the point in question, and then did this vector dot product between what we know to be the orthogonal vector and a vector which lives on the plane, expand, and you get what is, in this case, your tangent plane. If instead of calling this z, I called it L of x and y, we would call this a first order approximation. Okay, hopefully that made the explanation of a moment ago clearer. There's no reason in this context to do this. So if you handed me this function and said, find the tangent plane at the point 1, 0, 4, or when x is 1 and y is 0, I would do this. I would just jump straight to method 1 and do my normal computation. The reason why I want to emphasize method 2 here is because in our next example, method 1 isn't either, I can't remember which example is coming up next. I'll see in a moment. Either it's not that good or it's not even viable. So we'll take a look at that in just a moment. Method 1 is not viable for this example. So in this example, what we want to do is take the set of points in the xy plane which satisfy the equation y squared equals x plus cosine x times y. And if we can, write down an equation of the line tangent to the graph of this set of points at the point 0, -1. So we're looking at a picture of the graph of this equation. This is not a function. This is not the graph of a function. Y is not a function of x. It doesn't pass the vertical line test. X is not a function of y. It doesn't pass the horizontal line test. Looking at this expression here, you can't remotely try to isolate x or y algebraically either. So even if it was, even if it did pass the vertical line test and you could say y is a function of x, you can't solve for y so that you could then take derivatives and things like that. So what we have here is just an equation. It's not a function. It's just an equation. But we can still take the graph of this equation in the xy plane and think of this as a level set for a new function of two variables. So I'm going to imagine that this is a picture of the domain of some function h of x and y. I'm going to then be able to compute the gradient of h, evaluate that at the point 0, -1, and we will be able to write down our tangent line, even though method 1 in this case wouldn't work. So you have to use method 2 here in order to get the tangent line. It's actually going to be a very nice computation. Okay, so what I'm going to do is define a new function h, just like before, which is a function of x and y, so that what we have here is a snapshot of the domain of h. And how I want to create this function is I want the set of points x, y in the xy plane which make this equation true to correspond to a level set for h. So h has a domain which is going to be all of R2, for which this curve is one particular level set. We're going to do the level set h equals 0. I could subtract y squared over. I could subtract the right-hand side over. I'm going to do y squared minus x minus cosine of xy, like that. Okay, so all of the points which make this equation true, if you took the xy pairs, the xy values from the points that make this equation true and plug them into this right-hand side, you would get 0. So all of the points that make this equation true form the level set h equals 0. In other words, the graph of this equation is the graph of the level set h equals 0. And we know the gradient of h is going to be perpendicular along that level set. Let's compute the gradient of h in general. Okay, so gradient of h. In general, at any point in R2 would look like -1 plus y sine of xy, 2y plus x sine of xy. Like that. Okay, for any point in R2, you plug in x and y, you get the gradient of h at that point, but we're now focusing on the gradient of h evaluated along the curve in R2, which is the level set h equals 0, which is the graph of this equation. And in particular, I just want to focus on the point 0, -1. So let's see, we would get x is 0 is going to make the signs disappear. -1, sign disappears, -2. Okay. I'm just going to take a moment to check my work. So -1, sine xy, y pops out. Okay. 2y plus sine xy times x. Okay. And then when we plug in x equals 0, sine of 0 is 0. So -1, -2. All right, looks good. This vector, which I'm now going to add to the plot, is orthogonal to the level set. And hopefully you can really see that now in this picture. So this is orthogonal to the level set. So it's going to be orthogonal to the line tangent to this level set at the point 0, -1. We can now use the vector form of a tangent line or plane to write down the equation of that tangent line. So we'll say -1, -2. Oops. I keep getting ahead of myself. I'm like, it's going to be equal to 0. But first we have to dot it with x minus 0, y minus -1, so y plus 1. All right, let me just expand everything. We'll get -x minus or plus 0 minus 2y minus 2 equals 0. If you want to put it in a more traditional form, you could say y equals -1/2 x minus 1. Again, I'm going to check my algebra. So I brought the 2y over, left me with -x minus 2 divided by 2. Yeah. Okay, so that is the equation of the tangent line to this curve at the point 0, -1. And as you can see, this wasn't that bad. Algebraically, it wasn't that bad. And also, it was possible, whereas treating this like some kind of function was not possible. So we couldn't do, anything to do with the theory of functions on this equation because this is not the graph of a function. Yeah, I think I'll leave that there. I wanted to illustrate here how method 2 can be very useful. It's possible sometimes that you might have an equation and you could solve for one of the variables in terms of the other. A simple example would be something like x squared plus y squared equals 1. You could solve for, say, y and say, if you're looking at the upper semicircle, y is the square root of 1 minus x squared, but then you've introduced a square root into your expression, and that's going to make the differentiation messy. But if you try method 2, I'll let you do this as an exercise. If you try method 2 with x squared plus y squared equals 1, you'll find that it's actually much cleaner. You don't have to bring in any kind of square roots. The derivatives are going to be nicer. So there are contexts, not only where method 2 is the only method really that's viable at first glance, but also it would make the computations better along the way, even if method 1 was possible. Okay, let's look at another example. This is our last exercise in this lesson, so I thought we could have a little conversation about this. I'm going to give you things to think about and steps to do. Let you do them. I'll come back and take you through the answers. Hopefully that's just verifying that you did everything correctly. So what we are looking at is an equation relating x, y, and z. So namely, z to the fourth plus 2z equals x sine of y minus e to the x, y. Okay. My first question is this a function, not as it's written, but could you rearrange this perhaps to view one of the variables as a function of the other? And for that, it might be helpful to look at the picture. All right, looking at this equation, I wouldn't try to solve for any of those variables in terms of the other. X and Y, I think it's hopeless. Z, it seems very hopeless. Looking at the picture, if you see this tube right here, you recognize that the graph of this equation doesn't pass a vertical line test, horizontal, with respect to any variable. So certainly, globally, this surface object could not be viewed as the graph of a function. All right, so we are not going to try method 1 because it doesn't seem like it would even be viable. Let's jump straight to method 2. So my next task for you is to write down the function, which as you do that, make sure you identify what the variables for this new function h should be. All right, hopefully you wrote down either this or x sine y minus e to the xy minus e to the fourth minus 2z. Basically, you could take left-hand side and subtract it over or right-hand side and subtract it over. I subtracted over the right-hand side. This is a function of three variables, and if you look at how this function is defined, there are no restrictions for the domain. So you could think of h here as a function on all of our three, not just a function on this orange object that I've graphed, but h exists everywhere in R3. This orange object that we are looking at is the graph of the level set h equals 0. So every point on this orange surface is a point for which z to the fourth plus 2z equals x times sine of the y-coordinate minus e to the x-coordinate times y-coordinate. So this was the graph of an equation. We're now thinking of it as the graph of a level set in the larger domain for this new function h. Okay, our next step is to compute the gradient of h and then evaluate it at the point in question that's 5, 0, -1. That's just a computation, but go ahead and do that. We will come back and compare. This example is the rare case where writing the gradient as a proper vector, so here it's a 3 by 1 vector, is actually more space efficient for me because I ran out of room very quickly. So at any point in R3, anywhere you are here, if you want to stop right here and compute the gradient of h at this point, this would be how you would compute that gradient of h. We are interested in the point 5, 0, -1, which lives on this orange shape. And unless I made a mistake, -4 plus 2 is -2. It looks like this. Okay, so it just happens to be 0, 0, -2, which is really nice. While these zero coordinates are going to wipe out several terms, don't use that fact quite yet. Your next and final task is to write out the full dot product and then expand your dot product to hopefully get the equation of the plane, which is tangent to the graph of our starting equation at the point 5, 0, -1. Taking nothing for granted from these zeros, the vector dot product that we need in order to write down the equation of the plane tangent to the graph of this equation, the graph, this yellow surface, at the point 5, 0, -1, is this orthogonal vector, dotted with x, y, z minus the point 5, 0, -1. So that's x minus 5, y minus 0, z plus 1, z minus -1. This dot product needs to be 0. We're basically done. So let me take a moment just to talk through this dot product and why it works. X, y, and z here refer to any x, y, z coordinates in space. So any x, y, z triple that you would take from R3. The thing is, most of them, if you plug into this equation, you won't get 0. So this equation, this dot product here, will be 0 if and only if the x, y, z coordinates of the point that you plug in come from the tangent plane. So that's this vector form of a tangent plane. That's the most common context to learn this dot product, but it also works in general for other dimensional spaces like tangent lines and higher dimensional spaces that we could work in. Okay, to expand this, I could just expand it. I'll get 0, 0, -2z minus 2 equals 0. Basically, we're left with just this, divide over by -2, z plus 1 equals 0, so z equals -1. Am I out of room? No, I'm not. Okay, so for a very complicated shape and complicated starting equation, the tangent plane that we got to at the end was quite small. It's z equals -1. Why is it so simple? It's because actually, if you look at this point, the orthogonal sense of direction is completely vertical. So here I wrote down the orthogonal vector 0, 0, -2, because that's what I got out of the gradient of h. But that means that 0, 0, 1 is also orthogonal. So this plane is parallel to the xy plane. It's just shifted 1 unit down so that it lands on the point 5, 0, -1. All right, I hope that you enjoyed these examples. I know we started with some concepts that might have been hard to picture at the time, especially when we worked through method 2 for the first time. So if you didn't follow that explanation at the start of this video, having now seen the practice, how we actually use method 2 and use this knowledge that gradients are perpendicular to level sets, hopefully now if you revisit the ideas that we opened with, they will be clearer for you. Thank you for your attention.